Okay, Simon, I'm going to spotlight you and I'm going to go set up right now.
Okay.
So you guys should only see Simon now.
I can see you. I like that scene behind you, Simon, with the graphic.
In fact, my face is illuminated roughly the same as the planet. That's also very deliberate and coordinated.
Reporting live from the planet.
So, Jeff, I see you've got a whole load of certificates behind you.
I have the luxury of having had a home office for 5 years, so got it all decorated. They're not all mine, though. Just looks more impressive.
They look impressive.
The waiting's the hardest part.
Yeah. Yeah, I did think to put my phone in the other room in case any of the children called.
Smart.
And when my oldest called me yesterday, it was the questions like, well, if there's water on that planet, what kind of life would there be in there?
Okay, are we live?
Go on, Simon.
Okay, we're live. Well, welcome. Welcome to Facebook Live from the SETI Institute and from various other locations around the world. Today we're going to talk about Kepler 1649c, which is the discovery of an Earth-sized planet. Can't say Earth-like planet, we can talk more about that later, in the habitable zone around its parent star. And to talk about this, we have three guests and three people who contributed to the discovery. Jeff Coughlin from the SETI Institute, an astronomer here. We have Andrew Vanderberg, NASA Sagan postdoctoral fellow at the University of Texas at Austin, and late night guest from the UK, Pam Rowden from the Open University. So welcome everybody, and congratulations on this discovery, which was made using Kepler data. I wonder if, Jeff, you could start just saying a little bit about how Kepler makes its discoveries. Jeff, did you hear that?
You're back now.
Oh, sorry. welcome back.
Yeah, good work now.
Yeah. So tell us a little bit about Kepler, the Kepler mission, and how it actually discovers planets.
Yeah, so Kepler is a great mission. So it's a space telescope. So it's out there in space, way beyond the orbit of Earth. And it's kind of like Hubble, but it had a really specialized mission, and that was to find exoplanets, planets around other stars. And so the way it did it was for 4 years, it just stared at one spot in the sky. And it basically looked for stars that we'd be able to measure the brightness. And once in a while, we'd see them dim periodically. And the way to detect planets was that once in a while, a planet will line up just right, if you look at enough stars, so that it passes in between the star and Earth as we see it from Earth. And when that happens, the star blocks out some light. So by observing over 200,000 stars, you see some systems that happen to line up just right to transit, and we're able to detect those planets and find out what their size is and about how far away they are from their host star. And that tells us if these planets are similar in size to Earth, where we think they could be rocky and have a solid surface, and if they're the right distance to be in the Goldilocks zone, where it's not too cold, not too hot, but you could have liquid water possibly on their surface. And so Kepler was the first mission to be able to find planets that could possibly support life one day.
Okay, that's really cool. Just to let everybody know that please do write in and let us know where you're listening from or where you're viewing from. If you have any questions for the team, please let us know. Those questions will be passed on, and we'd love to answer any questions that you have about Kepler and about this planet or any planets, other planets that you are interested in. So the Kepler mission, as you say, it looks for the dimming of stars, and so it's staring at this one patch of sky all day, all night, waiting for these stars to dim. Is there a human watching this happen and trying to look for this dimming? How do you actually do that measurement?
So luckily, no, we don't have to stay up all night. We're kind of spoiled. So the data would come down monthly from the spacecraft, and so we get monthly data from it. And then scientists on the ground would start pouring through the data. And basically, you just get a measurement every 30 minutes of how bright the star is. And we write computer algorithms to detect when there are dips of light that occur. And when you see them equally spaced in time, 10 days, 10 days later, another 10 days later, oh, there must be a planet going around once every 10 days.
Mm-hmm. Okay. Now, Andrew, is it just planets? Are there other reasons stars vary in brightness? Stars aren't necessarily particularly stable things. Some of them are. We're lucky that some of them are very stable, including our one. Is there other things that can be seen this way?
Yeah, that's right. In fact, most of the stars in Kepler that we see dimming, those dimmings are not caused by planets. They're caused by other things like stars going around other stars. They're caused by things that happen on the telescope. So imagine a cosmic ray came in and hit your detector and damaged one of the pixels and caused it to be a little bit less sensitive. Or imagine that a micrometeorite came in and hit the telescope and jolted it just a little bit and caused everything to look a little bit wacky for a second. So all of these other things can happen, and it's a big job to go through and try to figure out which of those dimming events are caused by planets and which are caused by other things.
Right. Wow. And I imagine, for Jupiter-like planets, which are huge, this effect is obvious. But Pam, you're looking at Earth-like. I mean, the Earth isn't particularly a big planet, is it? So tell us about finding Earth-like planets with Kepler.
Well, that's where it really gets interesting. And Kepler's sensitivity was such that it's actually detected planets that, a few of them that go down to Mars size. But what it does is it looks for this very small dip. I think it's probably about 1/100% if it was the Earth around the Sun. It's looking for this really tiny dip. And the advantage we have with Kepler looking at something for 4 years at a time is there's a characteristic called signal to noise ratio. And the longer you look at something, the higher that gets. I mean, the noise is just like, noise. You got your kid in the flat below jumping around, and you've got the people playing on the drums and everything. You've got the noise, and you're trying to pick out the signal. And this is where the repetition that Jeff described, it really helps, because the more occasions you can see it repeat, the better the signal to noise. And there's a certain standard that the Kepler project had. It had to have a certain value of 7. And I believe the planet that we're thinking about, its signal to noise ratio was somewhere between 7 and 10 originally. I think it improved with all the work that Andrew did. But you can see how really close it was to the point where you'd say, nah, nothing there. It's been a lucky planet in so many ways that we've been able to see it. It's quite amazing, if that makes sense.
Yeah. So we've got a lot of people listening in. We've got people from England, Norway, Pakistan, Ontario in Canada, Scotland, Greenwich, that's Greenwich, Connecticut, Peru, Mexico, Kent, Almada in Portugal, and Chile. So we have people watching in from pretty much all over the world. A lot of people staying up at 10 p.m. in England as well. That's great, and Scotland. One of the questions comes in, and actually we can start talking about the planet itself now that we found. One of the questions says, is this exoplanet bigger or smaller than the Earth?
So,
of Andrew, yeah.
Yeah, so we actually can't tell. The most likely value for its size is only 6% larger than the Earth, but it could be larger or it could be smaller. We have some uncertainty in our measurement, and that uncertainty totally intersects the size of the Earth. So it's right around the same size, as far as we can tell.
Okay. And this system itself, the Kepler 1649, first of all, this isn't the first planet discovered around this star, is it? So tell us about its unsung sibling at the moment, 1649b. When was that found?
I think that was found in 2017.
Okay.
It was discovered by a team led by Isabel Angelo, who I believe was at UC Berkeley at the time. Mm-hmm. And they thought that there was only one planet in the system, but it was very similar to Venus in terms of its size, in terms of how much light it got from the sun. Mm-hmm. So we already had this star on our radar. And when we saw the second signal that Pam was able to pull out and look through in the false positives, it caught our attention immediately because we knew the star's history and we knew that it already had one planet.
Okay. Pam, tell us about this concept of false positives with Kepler. And, you know, one planet's discovered, and, you know, size of Venus, and we're saying this one's roughly the size of the Earth. These are two very similar sized planets, but one was found, that's great. And yet this other one sort of slipped through the net, as it were. Give us the story of that.
Okay. There were basically, Kepler had four categories of false positive. One was, it's an eclipsing binary, which is two stars, one orbiting the other, and it can produce a similar dip to a planet, but it'll be larger. Mm-hmm. There was another category which is called a centroid offset, which means you think this signal comes from this star. It comes from that one over there. It's just, you just think it comes from here. There's a fourth category called an ephemeris match, where you say, yeah, that exactly matches the signal we've got from this other star, so you know it's a different one. But the fourth one, which applies to this particular planet, is what's called a false alarm. And it's a case where the code that Jeff created looks at it and says, this does not look like a transit. There's something about it that looks a bit dodgy. That does not look like a transit. That was why this particular signal had failed. And in a lot of cases, that can be because the star's variable. So you've got the natural variability of the star, or it could be an instrumental effect, such as Andrew was talking about, the cosmic rays hitting. In this case, there were, this particular system wasn't observed for the whole period. I'm sure Jeff can give you the full history, but two of the quarters that it was observed for were particularly noisy, so that it was more difficult to pick up the signal. And also, I believe the area that they were looking at to begin with was just not quite right. But when I looked at it, when I was doing the individual vetting, it was a question of, I'm not entirely convinced that this is a false alarm as it was described. So therefore I brought it to the group, and Jeff and Andrew and everyone else working with it looked at it. And I think we had 2 sessions in total on this, but then we had this eureka moment when it's, hey, this is not a false positive. This is a planet, and it's not just a planet. It is one of the most amazing planets we found so far. So yeah, that's how this planet got designated as a false alarm and then got saved.
Okay, so the computer, the robot got it wrong. The computer got it wrong in a sense, and the human eye looking back over it actually dug this out of the weeds.
Yeah, that's right.
Exactly.
Yeah.
Yeah, the initial the automated analysis, at least it did flag it. So it flagged it as, oh, this is maybe possibly a planet. And then some of our other automated methods said, I'm not real confident, but it's likely a false positive. And so that's where it sat until Pam came across it. Well, again, major kudos to Pam, looking over thousands of these things by eye. And so she's scrolling through, oh, that's junk, that's junk. Oh, this one looks, promising. And then, yeah, when Andrew applied his analysis and said, oh, the automated method didn't do things optimally, let me do a better job. All of a sudden it popped out much cleaner. And that's when Andrew did his work, was like, oh yeah, this thing looks like a real planet.
That's great. It shows the importance of, again, the human brain as an analyzing tool, even these days, is fabulous. Yeah.
It's hard to beat.
Yeah. We have a few more people, locations: Australia, Alberta, Belgium, Cornwall, Montana, and we got a few more questions here to throw to you guys. First of all, from Jim, how far away is this new planet from us?
It is about 100 parsecs, which translates to something like 320 light years, 330 light years. That sound right?
Okay. So does that make it sort of closer or a typical distance for a lot of these exoplanets that are being discovered by Kepler and other missions, or is it quite a way out?
It's pretty close by for something discovered by Kepler, but it's not particularly close for some of the new planets that are being discovered by NASA's successor mission to Kepler, which is the Transiting Exoplanet Survey Satellite, or TESS. TESS is finding planets that are even closer to us. So if we had found this, before TESS existed, we would have said, wow, this is really close by. But we've gotten a little bit spoiled by TESS in the most recent years.
Okay. Question from, this one's from David. Any chance of spectral analysis of this planet, or is it too dim and far away? So now we're looking at the moment, what information have we got from these observations, and what information could we potentially get about this planet?
Yeah, so from the Kepler observations, the main pieces of information that we get are the size of the planet, so how big it is, and what its orbit is like, so how far away from its star it orbits, and based on that, what temperature it roughly is at. So based on all of those pieces of information, it seems pretty similar to the Earth. It gets about the same amount of light as the Earth does, a little bit less, and it is about the same size as the Earth, identical as far as we can tell. When you start asking more detailed questions, like what are in its atmosphere, and is the planet, rocky like the Earth? Does it have the same type of core mantle structure that the Earth does? That's a lot more difficult. And it may be a long time before we can answer those questions about this planet in particular. And the reason is that it is a little bit faint. It's about 100 parsecs away, which is not the closest planet we've ever found, but it's not too far away. The real problem is that the star itself is very, very dim. It's a very small star. It only is about 0.5% as bright as the sun. And that just means that our telescopes can't get much light and get much information about it. So we'll need a really, really huge telescope to be able to answer the more detailed questions about what is in its atmosphere and what does the spectrum of the planet look like. Maybe in the future, but it'll be a while, I think, before we can ever learn anything like that about this particular planet.
Okay, cool. And as you're saying that, we're saying this is an Earth-sized planet and not an Earth-like planet. And one of the reasons is that the star is not a sun-like star, is it? But Pam, what if you were standing on the surface of your newly discovered world, with your flag, how would it look in the sky? How would this be different from standing on Earth and looking at our sun? And this is speculation, of course, a lot of it.
Yes. Yeah. I mean, one of the things we speculate is that, how the moon is tidally locked to the Earth, so it's always got one face facing the Earth. This planet, it's only got its year lasts 19 of our days. So there's a possibility there that this planet is tidally locked, so that one side would always face the sun and would be rather warm. Another side would never see the sun and would be rather cold. And then there'd be a strip in the middle where you might get some daylight and crossing between. So what it's like when you're standing on the planet might depend on what side you're on. It's of a temperature where we would expect that if there is water around, you'd have liquid water. I'm not going to say you're going to have a lake or an ocean or anything like that, but you could have liquid water. And there's this beautiful artist's impression that NASA has done, where they've done clouds in the sky and rocky landscape. And I think that's probably a fair summary. But yes, what you will see will depend on whether you're on the day side, the night side, or the twilight zone in between. So if I can use the phrase twilight zone.
You can with the SETI Institute, yes. Yeah.
Yeah.
Yeah, okay, that's wonderful. We got people from Tunisia and Germany joining us, so welcome. There's a question from Amal. What is Kepler most famous for? And I'm not sure if that's Johannes or the spacecraft. So Jeff, you can answer that however you like.
I'll answer both. So Johannes Kepler did a lot of work in figuring out the laws of planetary motion and figuring out that, you know, planets orbited the sun, and they did so in an elliptical fashion. And so since the Kepler telescope was a planet hunter, it was named after Johannes Kepler for that reason. But yeah, Kepler is really famous for finding planets. As you touched on earlier, talking to Andrew, it's also found all sorts of fascinating stellar systems and white dwarfs that are evaporating planets and lots of cool discoveries. But it's mostly known for being a planet hunter. And so we found we have over 2,000 confirmed planets from Kepler now. There's about another 2,000 that are just candidates, which means we're pretty confident they're a planet, just not 99% confident yet. And so it's just found an incredible amount over the years. And, you know, as we're seeing, the thing launched over 11 years ago. The primary 4-year mission ended 7 years ago. And then it had an extended mission called K2 for another 4 years. But this planet that we pulled out was in that original data set. And so we're now 7 years past the end of data collection for the primary mission. And when we just found this thing. So who knows what else still remains to be found in the data. I'm hopeful even more exoplanets will be pulled out with time.
Okay. So Pam, your work's cut out for you. Yeah, I mean, you can't retire yet. Are you?
Not yet. No.
Are you still going through the data? How are you doing at the moment with this? I mean, you may have gone a little bit crazy looking at light curves, but is this still an area that fascinates you?
Well, yes, absolutely. I mean, the Kepler False Positive Working Group has finished its work where we looked at every object that had been designated a false positive, and you decided if you could be convinced what type of false positive it was. So yes, but I'm now as a volunteer light vetter with the test missions that Andrew was talking about. So I'm continuing to look through light curves, but just of a different mission. And but yes, I do believe that Kepler may well have more surprises to bring out and to discover, if that makes sense, because there's an awful lot of data there. And as Jeff said, there's not just the main mission, there's the K2 mission as well that people are finding things in. And as well, the Europeans have the Plato mission that's due to launch in 2026. And they've got the Cheops mission that's just gone up that's going to look at characterizing the exoplanet atmosphere. So there's an awful lot going on both sides of the Atlantic that we can really discover and learn. And I believe the Twinkle mission is planned as well, which is, it's not an acronym, it's quite surprising, but Twinkle is, again, aiming, I believe, to characterize different missions. It's an amazing time to be someone studying planets and studying astrophysicists.
Yeah.
You've probably seen from the view, I'm a little bit older, and when I was a child, I remember learning the names of all 12 moons of Jupiter. You couldn't do that now. You know, we know so much more. It's just so amazing and fascinating. It's just an amazing time to be in astrophysics.
So that's that. So is this something as this is a question for all three of you. You know, you're involved in discovering new worlds, which is probably something that nobody thought you'd be doing 20 years ago. Was this a childhood ambition to become an astronomer? Or is this, you know, what you wanted to do? Pam, you said that that's perhaps, you know, besides memorizing the moons of Jupiter, which is trickier now because there's sort of 73 of them or something.
Yeah.
You know, is this sort of a childhood dream?
I was always interested in astrophysics. I did my first degree back when I was young in history. Then I got married, then I had children, then you're raising the children. And then my two sons had gone to university. My daughter was living her own life a bit more, and I had a choice. I could be one of these mums who never leaves her children alone, or I could get an interest. So I got my bachelor's degree with the Open University, distance learning. And when I'd finished that, I just couldn't give up the astrophysics. So I managed to get a PhD position, fully funded, again at the OU. And that was, my thesis was on false positives and shallow eclipsing binaries in transiting exoplanet surveys. So being invited to be part of the Kepler False Positive Working Group was absolutely amazing. But yeah, I had dreamed of it as a child, learning more about the stars. It's great to do it now. It doesn't matter how late it is, you can still follow your dream and learn and be part of something. And 20 years ago, I'd never have thought that I'd have been discovering planets. It's absolutely amazing to be where I am now, if that makes sense.
Yeah. Oh, absolutely. Absolutely. What about Jeff and Andrew? Is this this started off young?
Yeah, for me, I always had a big interest in physics and liked it. But when I went to college, I thought I was going to go to med school.
Okay.
And so I was taking, you know, the chemistry and biology, and I was like, this is okay. But then I took sophomore year, I took an astronomy class, and I just kind of went, wow, okay, I really, you know, everything else was cool. I am fascinated by this. And ever since then, I've been bitten by the astronomy bug.
Yeah.
So yeah, for me, it started off there. But I remember when I was writing essays for grad school, this was back in about 2006. I vividly remember writing in an essay of, you know, what I would love to do one day is to be part of a team that can discover another planet, you know, similar to Earth. And if I can just help in some small part to do that, that would, you know, really make my life. So to be here now, having now been a part of that, is just, it's incredible.
Yeah, yeah. You can now retire. You've done it.
That's right. See ya.
Andrew, similar story?
Yeah, similar story. I always had an interest in astronomy. I didn't necessarily think of it as something that I would do as a career until college, when I took a class like Jeff and realized this is really awesome. And took some more classes, went to grad school. Here I am.
Yeah. Cool. Well, we've got a couple of a few minutes left. People calling in from or signing in from Louisiana and from Bulgaria and Chicago. There's a nice sort of spread. A couple of questions from Danut. One is, can the James Webb help get more details? First of all, maybe with this planet, you said maybe tricky, but in terms of what the James Webb, which wasn't initially designed to look at exoplanets, but it seems as though it's going to be a powerful tool now. Anyone like to address James Webb?
Yeah, so James Webb could certainly observe this planet. I think that the main thing it would tell us is much more precisely how large the planet is. So I said we know that it's probably about 1.06 times the size of the Earth, but it could be a little bit larger, it could be a little bit smaller. James Webb would really help to nail that number in stone and tell us just how close it is to Earth in size. In other systems, James Webb may be able to actually look for molecules and atoms in the atmospheres of planets. Probably this one is too hard just because the star is so faint. But for nearby stars, like the ones in the TRAPPIST-1 system, or the planets in the TRAPPIST-1 system, we could potentially start looking at molecules and atoms in the atmospheres of those planets and try to figure out whether they really are anything like the Earth, whether they have some of the constituents in their atmospheres like we have here, or whether their atmospheres are even there, whether they've been totally stripped away by the environment that they live in, very close to a young active star. So it'll be a really exciting time for everyone who likes exoplanets when James Webb launches, and we can start answering some of these questions that we've wondered about for a long time.
Yeah, great. One other question, the star's very dim. Does that mean that it's dying? I mean, we don't want to get into sort of stellar astrophysics here, but is there an estimate roughly for the age of this star? Because that's quite important if we're talking about life, which, you know, takes a long time to maybe come about and evolve. How old is this star? Have there been estimates on it?
It's really hard to estimate how long stars live if they're not particularly young. As far as we can tell, this one seems to be old, possibly the age of the sun, possibly older. What we can be sure of, though, is that it'll last a long time. It is burning its fuel very, very slowly. That's why it's so dim. But that means that it'll have a long time to keep burning its fuel, and it'll last way longer than even our own sun will.
Okay. Yeah, these red dwarfs stick around for a very, very long time, don't they?
Some of them can be like trillions of years.
Trillions of years. Yeah.
It's mind-boggling.
Yeah.
Okay, here's an interesting question. Maybe a good one to wrap up, as this is the SETI Institute. If you guys had to choose one exoplanet to recommend for detailed examination by radio telescope, what would you aim your telescope at, apart from the Earth?
I'll pick this one just because we're talking about it right now. But I mean, this is one of the closest in size and amount of energy from its star that it receives that's been found to date. So it's certainly, if not the top target, one of the top targets. But the great thing is we don't have to pick just one. You know, the SETI is looking at everything that we can and all the most likely places to look for any signs.
Yeah, cool. And what next? What would be a good discovery next? Should you be able to choose what you're allowed to discover? What's the next phase of, you know, excitement in exoplanet discovery?
I would love to find a planet just like this one, but about 10 times closer to us.
Okay. Yeah.
Because then we could really, as Andrew was saying, really get the details of exactly if it has an atmosphere or not, what that atmosphere is made of. Maybe even detect if there's water or hydrocarbons or anything else that'd be really tantalizing.
Yeah. What about you, Pam?
Yeah, I'd go with understanding the atmosphere of the planets as well, because it's one of the ways that we believe that we might be able to detect life is by determining what's in the atmosphere. Is there oxygen, methane, that kind of thing? And all the missions that are going up that are going to examine the atmospheres, they're the ones that, I mean, okay, they'll start with the gas giants, but then eventually at some point we're going to get to the point where we can actually look at these rocky planets and say, yeah, I can see water and things like that. So maybe 20, 30 years time. Yeah. That's what we'll be talking about. It's an amazing time to be an astrophysicist at the moment. We're just discovering so much.
An amazing time also to become an astrophysicist.
So fascinating. Yeah, and by the way, credit to Jeff for devising the RoboVetter program that automatically vetted all these planets and analyse them, because without that, then there wouldn't have been all the data for myself to look at and bring to group, and then for Andrew to do or work his magic with his code. So without Jeff, we wouldn't be anywhere, if that makes sense. So,
what I think so
all credit
incredible
to
is
Jeff
the sheer
for,
number of people involved, starting from the people who conceptualized the mission and designed it, the people that built the spacecraft, the people that flew it and got the data down, the NASA archives that stored it. This particular star was selected by a guest observer, so it wasn't in the initial main Kepler list. Somebody actually requested to add it as part of a big program, so without them, we wouldn't have had it. The team that wrote the pipeline to find the initial signal, the RoboVetter flagging it initially, false positive following up on it, Andrew studying and publishing it in detail. And so you got this huge chain of people without any one of which would have never found this thing. That to me, that teamwork is, I think, the most incredible aspect.
That is a big thing about modern science, isn't it? It's a team effort. It's so rare these days that it can be one individual. It's everyone working together with a different skill set, you know, astronomers, engineers, computer scientists, and so on. It really is a team effort. Well, if you want to read more about this amazing planet and its discovery, go to our website. We have links, we have some nice images, and check in, and we'll, you know, if there's any other discoveries, we will be reporting them as well on the SETI Institute page. Thank you very much, the three of you, for having a conversation. It's a fascinating and wonderful discovery. And we will see everybody soon. Take care.
All right, we stopped the stream. Awesome.
All right.
Good job, guys.
Thanks.
Cool, fantastic, Simon. That was fun.
Yeah.
So, Jeff, you're going to be staying a little later and
Sure.
help me do a little video, right? Yep. Okay.
Yeah, no problem. We'll just hang out here.
Okie doke. Nice to meet you both.
Good to meet
Pam,
you too.
good luck. You can
nice
go to bed
to see
now.
you too.
Bye, you guys.
Yeah, thanks to you both for joining. That's awesome.
Bye.
Bye-bye.
See you later, Simon.
See ya.
Nice to catch up with you all.
All right.
Okay.
That's-
So, I would. Can you tilt your camera down a little bit so you're not? You look a bit kind of small. There you go.
Sure. Yeah, I can get closer.
Oh, but then that light. It's weird, huh?
Yeah, lights. I can. It's a standing desk, so I can make it standing real quick if you're in no rush and see if that helps. So
No rush. Just want to make
Go
sure
on
you
now.
don't look too tiny in the video.
Yeah.
Oh no, I'm not sure that's better because now
Yeah,
that
that's
light's
more
right
like
behind
that,
your
yeah.
head.
Okay. I'll just scoot in closer.
Yeah.
So that's, if I get it there, it gets right there.
Interesting. Okay. Yeah, that's good.
Yeah,
So okay, so you can do your message, whatever you were saying before, but this just give me like before you start,
Mhm.
like whatever position you're in, you're sitting, just give it like a 1-2 count, and then when you're done with your message, also give me a 1-2 count before you move. You know,
Okay.
that way I have a nice cut in and cut out.
Okay. Just silent.
It's already recording, so you can do it whenever you want.
Okay. I remember what I was going to say. That's what thanks for. That's right. Thanks for helping us find new exoplanets and further the search for life in the cosmos.
Cool. That was great.
Cool. Okay. Yeah.
Yeah, we're just gonna cut them all together when we're done.
Cool. All right.
Awesome. Thanks, Jeff.
Good deal. No problem. Thank you.
All right. See you later.
All right. Thanks so much. Bye. Always the